Welcome back to Physical Science 20. This is section 1.3, heat capacity. There's quite a few objectives here, so it'll be 2 or 3 videos. Explain what is meant by specific heat of a particular substance. Compare in quantitative terms, so with numbers, the heat capacities of common materials including water, and explain how heat capacity can influence choices of materials used in development of technologies related to clothing, food, and shelter. Calculate the quantity of heat, Q equals mc delta T, when given mass, specific heat, and the temperature change to solve word problems involving this concept. Explain what is meant by the principle of thermal energy exchange to solve problems involving this concept. And explain the concept of thermal expansion and contraction of matter during heat transfer or temperature change, and describe some real-life applications. So, if you take a look here, have you ever warmed up a pot of water on the stove to make soup? If so, you may have noticed that it takes a long time to heat water up. The pot itself gets warm really quick, but the water takes a while. However, if you've tried to warm up the same amount of oil in the same heating conditions, you would notice that the oil warms up way quicker. Conversely, if a pot of water and a similar pot of oil at the same temperature are left on a stove to cool down, the oil cools down faster than water. So why is that? It all has to do with specific heat capacity. It takes more energy to increase the temperature of a kilogram of water by 1 degree C than it takes to increase the temperature of the same amount of vegetable oil, 1 kilogram, and to heat it up by 1 degree C. The amount of energy required to raise the temperature of 1 kilogram of a particular substance by 1 degree C is called the specific heat capacity of that substance. So the amount of energy required to raise 1 kg up by 1 degree C. The specific heat capacity of water is 4.18 times 10 to the 3. So I paused the video and just changed that. Make that change in your notes too, please. For some reason it wasn't in scientific notation. So 4.18 times 10 to the 3 joules of energy to raise the temperature of 1 kg of water by 1 degree C. Vegetable oil has a heat capacity of, and I'll make this change here, 2.0 times 10 to the 3 joules per kilogram degree C. Please make that change there too. And I guess up here I need to make that change there as well. They're just like magic, I made that change there as well. So 4.18 times 10 to the 3 joules per kilogram degree C for water. And it's a little bit less, you can see here, for vegetable oil, 2.0 times 10 to the 3 joules per kilogram degree C. So again, the amount of energy required to heat up 1 kg of substance by 1 degree C. So on the next page you can see a pot containing 1 kg of water at 10 degrees C uses a little more than twice as much energy to reach 100 degrees C as a pot containing 1 kg of vegetable oil at 10 degrees C. This difference occurs because water and vegetable oil are composed of different types of molecules. Different molecules require different amounts of energy to increase their kinetic energies, their moving energies, by the same amount. So that's an important thing to highlight. Specific heat capacities also represent how much thermal energy is released when a substance cools down. So vice versa, when something cools down, how does it release it? Table on the right gives specific heats of common substances. So if you look over here, specific heat capacities, the amount of joules to change at 1 degree C, and when we're dealing with 1 kg, as you can see, water is at the top of the list. It takes the longest to heat it up or cool it down when releasing energy. Then you have ethyl alcohol, ice, etc., all the way down the list. All right, quantity of heat. The total amount of thermal energy transferred from a warmer substance to a colder substance is called quantity of heat. Let's highlight that. So the amount of energy transferred from a warmer substance to a colder substance. A quantity of heat calculation takes into account, well, how much we have, because these numbers here represent 1 kg and 1 degree C. But what if we don't have 1 kg? And what if we don't have a change of just simply 1 degree C? Then we need to change the specific heat factor by those amounts. So Q equals mc delta T is how we do it. Where C, we can do this up here as well. Let's write down C in quotations, because that's what this is. Specific heat capacity is little c in this equation here. And then we're just If I have more than 1 kg, multiply by that. If I have more than 1 degree C, multiply by that. Delta T is the change in temperature, of course, by how much the temperature raised or decreased by. C, joules per kilogram degree C, taken from up there. And mass, of course, has to be in kilograms. Q gives us our joules amount. Note that if an object absorbs energy, its final temperature is greater. So if you absorb, temperature is greater. However, if you release energy, temperature is lower. So you'll have a negative value for delta T. Okay, so if you look at this third page, we'll do some examples dealing with this. When 200 mils of water is heated from 15 to 40 degrees C, how much thermal energy is absorbed? Now, I give you the substance here in milliliters. The density of water is 1 gram per milliliter, so we can easily figure out how many kgs that is. So if I look over here, we kind of know mass by knowing the volume. So 200 mils, and for every 1 mil of water, that's equivalent to 1 gram. Okay, so that's going to give us 200 grams, and of course, since we know that there's 1,000 grams in a kilogram, let's move the decimal 3 places to the left, and it's 0.200 kilogram. So 1 kg is equal to 1,000 grams. Right? Initial temperature, we started off at 15 degrees C. Final temperature, we end up at 40. Therefore, change in temperature is going to give us 25 degrees C. And little c, if you look back on our table there, we'll see that 4.18 times 10 to the 3. 4.18 times 10 to the 3 joules per kilogram degree C. So we know our units are right, degree C, kilograms and kilograms. So Q equals MC delta T. So our mass in kgs multiplied by our specific heat capacity and change in temperature. So you'll see here that this unit is joules per kilogram degree C. This is kilograms, so the kilograms cancel. Degree C in the bottom cancel with degree C on top, so we're left with joules as a final answer. 20,900, I believe, is the answer there. Or if you want to, you could put that in scientific notation. You don't have to, though. 2.09 times 10 to the 1, 2, 3, 4. All right, so that's how you do that. Not too bad. Let's look at the next one. An empty copper pot is sitting on a burner. The pot has a mass of 1.2 kgs and is at a temperature of 130. The pot cools to a room temperature of 21 degrees C. So you can see there we're releasing energy, whereas here we're absorbing it. Okay, so that's a key thing to note. So here you get a positive number, right? Maybe we should put that. Positive, since absorbing. Whereas this next one, we're going to get a negative answer. So M is 1.2 kgs. TI, originally we're at 130. TF, we cool it down to 21. C for copper, 3.8 times 10 to the 2. Joules per kilogram degree C. If I look at delta T, I skipped that for some reason. T equals T final minus T initial. So 21 minus 130. So you can see, here's where the negative comes in. Negative 109. So don't just think you have to take the bigger number, subtract the smaller. It's always T final minus T initial. And Q, of course, is what we're looking for. Okay, so our mass is 1.2, specific heat, and temperature. So if you type that in, 49,704 joules. If you look here, there's 2 sig figs though, so we'll round that off to 2 sig figs. So keep that. That's a 1/7, so that gets bumped up to a 50. But be careful if they include 2 sig figs. So this one may be better to write in terms of scientific notation, 5.0, because you can easily see the 2 sig figs. And then this decimal needs to move, let's see, 1, 2, 3, 4 places to the right. Okay, I think I'll stop the video there, then we'll come back and do this question. Then I have one we're going to add into here. All right, see you again.